Hello everyone, welcome. Today we're going to do a quick tutorial on how to do the easiest backpropagation um, algorithm, and hopefully by the end of this video you'll have an idea how to create your own network and do some really cool stuff with it. So for starters, I thought I would do a quick demonstration of the kind of thing you can do with a neural network. So what you're seeing right now on the screen is a browser. I programmed a small neural network. It consists of 900 input neurons, uh, 40 neurons in the one hidden layer, and then the output layer just contains 10 neurons. The 10 neurons correspond to the following digits, 0 through 9, you'll see on the screen, and the boxes next to them just will light up red or black, indicating whether or not the network thinks the digit belongs to that category. So when I, for instance, draw on my screen something like a 2, what the network should do is light up bright red right next to the 2, telling me that it thinks this handwritten digit, which I just wrote with my own hand, is a 2, which it does. Great. Similarly, if I draw something like a 1, my network should output a 1, as we would expect. Let's try a 5, and it thinks it's a 5. Cool. Very nice. We can try other digits too, just to show you. If we do like a 3, it thinks it's a 3. Okay, so that's pretty cool. This is really cool. But and the interesting thing about this program, this neural network, is that I made it all in just plain vanilla JavaScript, no third party, no PyTorch, no nothing. It just is my own library, my own code. Anyone can do this at home. You don't need any special hardware acceleration. You don't need the fancy NVIDIA graphics cards to do this. You can do this at home on your own computer. It's really simple. I'll show you how in a minute. But first, before I do that, I just want to give you a little background of how this program works. In particular, I had to make my own data set. So I did not use the MNIST data set. I had to create this little black box and store and hand write my own digits into it painstakingly, and then train my network on my own handwritten digits. So in some sense, I'm kind of cheating because this network is probably very good at recognizing my handwriting. The other thing that we should note about this network is it cannot recognize things that like scale, translation, and other uh, forms of variance. So like if this image was too noisy and I kept adding little bits and blobs here, you see it already fails because it doesn't know how to recognize this. This is not an image it's seen before because my data set has no noise, and so it doesn't know how to recognize this. And the other thing is translation. If I have a 3 over here, it's not going to recognize it. It thinks it's a 5, and that's partly due to because all of the digits in my data set are centered in this black box, and that's how it recognizes them. So when things are outside of this black box, it can give you any kind of a random output. Now, to work around this problem, we'll have to implement something called a convolutional neural network, which is way beyond the scope of the video I'm going to show you, and we're not going to do that now. So anyways, that's a quick introduction of some of the cool things you can do this. These neural networks are the basis and the foundation for things like large language models, image recognition, generative models, anything you can think of that modern AI can do. This is where you start off. It's the very basic networks. They're all capable of doing this sort of thing. 6, cool. All right, so let's get started. I want to look quickly at a couple of things here. Hold on, I have to find. Before we start, I wanted just to look at the backpropagation algorithm that if you go on Google and you type in on Google, this is what you'll see. It is the most indecipherable thing ever, right? This formula, the way the most people write it, if you go on Google Images or if you go on YouTube, this is how most people will have the video. It is almost completely unusable or indecipherable. To the average person, to the average eye, this is, you can't make sense of this unless you have a PhD or whatever. This kind of mathematics is just a total mystery, right? Here we go again, same thing. Another kind of image that if you're, once again, a regular person, this won't make sense to you. And then I found another tutorial where they're talking about gradient descent, backpropagation, they're doing the chain rule, all of that. If you've studied neural networks, you've probably recognized some of the terms I used. Stochastic gradient descent, you have your error function, all of this, right? And if you're not familiar with this kind of notation, if you haven't taken like a calculus course, this is really puzzling. How do you get these derivatives? What does this mean? How do you decipher this? Here's another example. People love to insert their own symbols and use fancy terminology that most people don't understand. And that's the last image. Let's take a look at the algorithm that I came up with that is much easier. Okay, this is so to start off with, to do all that fancy stuff, including the earlier example of doing basic digit recognition, which can be extended to facial recognition and all the other things that these AI models can do, we're going to start off with a really simple model. It's going to be a single neuron with 4 weights. There's going to be 3 input samples. This is our input data. The data will feed into our neuron. And then we're going to use backpropagation to adjust the weight values so that we get the correct targets. Well, how do you do that? Well, first of all, you start with by randomly selecting your input. In this case, we selected P1, which is our picture 1, and each I1, I2, I2, I3, I4 is a different value. So it could be like 0.12, negative 0.283, whatever. And we input that into our the input of our neuron, and then we multiply each input by its corresponding weight, and then we sum that all up and pass it to an activation function. So let's see what that looks like. If we zoom over here, we take our I1 times W1 plus I2 times W2, I3 times W3, I4 times W4, and then we add this entire thing up. That equals A. A is going to be the output of our neuron. Next, we have to pass it to an activation function. The reason why we pass this to an activation function is because the model has to be nonlinear. If your model stays linear, you won't be able to make a network that can really do a whole lot. It will only be able to differentiate between linear data, or what they call linearly separable data. You don't need to know what that is right now, but the core idea here is you have to have a nonlinear function. I've chosen to use the tanh function, the hyperbolic tangent, as it's sometimes called. I like this one a lot. It's easy, it's simple. Most programming languages have this as a keyword included in their in their programming language. And then once we pass this through our activation function, which you see here again, here it is, you sum that all up, we get our new A term. And then all we have to do now is get the error term. To get the error term, we get our A term, which we got by passing our sum through our activation function, and subtract it from some target. In this case, since we only have a single neuron, our target can be anything we want. And ideally, our target should be a value that is between -1 and 1, since that is the range of our function, which is the hyperbolic tangent. And that value should correspond to whatever is in the image. So if we are trying to tell the difference between cats and dogs, and P1 was an image of a cat, we should set it to 1 or -1, whatever you want. But as long as all cats are assigned a value of 1, a target value of 1, they should all stay at 1. And if they're assigned a target value of -1, they should all stay on a target value of -1. Similarly, image 2 or P2, picture 2, if that's a picture of a dog, if picture 1 is 1, this one, picture 1 is target value has 1, picture 2 is a different picture, should have a target value of -1, or whatever value you like in order to tell the difference. So that's, now that we have that out of the way, we have our error term. To update each weight, once we've passed our input value, we've done our summation, passed it through the activation function, and now we have our error term. To update our values, our weight values, we take our old weight value, subtract it from LR. In this case, LR is our learning rate, and we multiply it by our error term, or LR, I'm sorry, we take our old value, our W1, which is our first weight, and subtract it from this entire term, which is our learning rate times our error term times the input to the neuron. The input to the neuron of this, where this weight is connected to. In this case, it's I1. For W2, it would be I2. For W3, it would be I3. You get the point. It's all corresponding to each other. And you update these all at once. So you don't just update one and then feed the sample in again and update the next weight and the third. You do them all at the same time. Next, what you have to do, now you've updated. Now the model will only get a little better. So it's not going to improve dramatically over the course of a single iteration. You will need many more iterations for it to converge. Converge is just a fancy term meaning that the model settles on a solution that is acceptable, or has a low error. So then we feed it the next picture, 2 or 3. You can go in order or you can go randomly. I prefer to go randomly, choosing these P1, P2, P3 at random, making sure they go to their corresponding output values or target values and updating the weights accordingly. So if we put in, let's say, picture 2, we've selected picture 2, you do the same thing, put them in your inputs, multiply them by their corresponding weight, add all of the samples up, pass them through your activation function, get your error term, and then update your weights. And in this column, you'll see I1, I2, I3, I4. We just changed these to our new input sample. So our new input sample would be image 2, and our variable names for image 2 would be D1 through D4. And they would, of course, correspond to the weight values of our neuron. So that's all. That is all you need. You don't need any derivatives. You don't need anything. You don't need fancy hardware. That is enough to get you a neuron that can tell you the difference between basic images. So if you wanted, like this neuron, for instance, if you're using the hyperbolic tangent as an activation function, which I am, I could get it to tell me the difference between 2 digits, ideally. You could do more and try to squeeze that in, but it's not very smart. You should only really, if you're doing classification tasks, you should only have your neuron tell the difference between 2 classes, not many classes. Okay, so now that's out of the way. Let's talk about some constraints of every network that you'll face if you want to get these things to perform the way that they're supposed to. For instance, 1, weight values must be within range. For tanh function, weight values should be between -1 and 1. Well, that makes sense. If we take a look at our hyperbolic tangent here, we'll see that, hold on, just trying to move it. I'll look at our tanh, which is our hyperbolic tangent. I'm using Desmos. It's a program that allows you online that you can go and type in all your functions and do lots of cool math. If we look at tanh and the range between which the function is able to give you as an output, we'll look, it can go between -1 and 1. So naturally, we would expect that the input value should all be between that range, as well as the weight values. And the reason why we set the weight values to the same range as our input values, the idea is that when we do our the dot product or matrix multiplication, as it's called, the output will hopefully still be confined between the same range of our function, which is in this case -1 and 1. Now, for other functions like sin x, it's the same thing. Because the maximum is going to be 1, minimum is -1. So the input value should be between that range, and the weight value should be initialized between that range. Same thing with tanh. Cosine, same thing. It's just phase shifted, like, I don't know, 90 degrees. But the maximum and minimum values are between -1 and 1. If we look at this is called the Rayleigh function. It's the linear rectifying unit. For this function, you will have to make sure that your target values, your weight values, and your input values are all between, let's say, 0 and 1 or 0 and 2, whatever you like. As you can see with this function, any negative value just goes to zero. And so if you input a bunch of weight values in that range or below zero, so any negative value, it'll just be equal to zero and it'll become non-differentiable and your model will fail to converge. Okay, so we got that out of the way. Let's look at let's continue with the discussion about some of the things that are required for your network to work. This is universal of all networks, by the way, and even especially the simple ones, but as your networks grow in size and complexity, additional rules will have to apply. That we won't go into that within the scope of this video, but let's look at some of the things that you will need to do if you want to implement a network like I have to recognize basic handwritten digits. All input values must be within your activation function's range. For tanh, cosine, and sine, it should be -1 and 1. Activation function must be differentiable, otherwise we will reach saturation conditions. A saturation condition, let's go back to our function and look at our tanh. If we have values that are too big, what will happen is we'll end up really far to the right, really far to the left, depending on our values. And the further right or left you go for the tanh function on our graph here, you can look that the range will go to either 1 or -1. It won't approximate, technically it approximates 1, but your computer will just round it off to 1. And at this point, you can see if I step slightly to the right or slightly to the left, the value remains at 1. Well, that's undifferentiable, and the network won't be able to change the weight values in a way that's helpful. Because there's no way for the network to tell when it makes a small step to the right or left whether or not that was helpful, because either way it goes, it's going to be 1. There's no update that's helpful. So that's a saturation condition, and we want to avoid that because your network will not converge if that happens. The learning rate, LR, learning rate. This is just a constant. It should be very small, between 0.1 or even 0.01. Of course, you can make this value larger or bigger. If it's larger, your network will likely diverge. And so if it diverges, your network essentially fails. It won't work, and you'll have to restart. So you don't want it to be too large, but it will be fast. So you want it to, the larger the learning value is, the quicker the amount of time it will take for the network to learn. The smaller the learning value is, the learning rate value is, the more accurate it will be. You're pretty much guaranteed that the network will converge, but it will take more iterations and more time. So you have to learn what kind of balance you want. Also, with a very large learning rate, say like 1 or 2 or 5, your network won't always just diverge. It can also oscillate. So instead of going to infinity with every weight value, which won't converge on anything useful, it'll just jump around between values and just oscillate, which is of no use to you either. The network will only converge after many iterations. Yeah, so like even with this tiny network that has 4 weights and 3 input samples, you still will have to run it about 500 to 2,000 times, even with a relatively large learning rate value, which is, in this case, will be set to 0.1. And only after that many iterations will the network converge. Then you can feed in your samples and measure the output versus its target and see if it's performing the way you want it. Of course, for larger networks with more layers that do more complex tasks, that tell apart more things, you're going to need more parameters, and it's going to take a much larger time and more data, of course. And this is the input data should be selected at random. This is sometimes called stochastic gradient descent. Like I meant, it's a fancy term that just means we select our input sample at random, and we do that over and over and over for 500 to 2,000 iterations in this case, and then your network will converge. Don't be intimidated by this fancy term, stochastic gradient descent. In this case, our gradient is our error term. Stochastic means we're selecting things randomly, and descent just means we're going down the curve of the error function. It's a little hard to describe, but that's all it is. This is it. This is more than enough of what you will need to create even surprisingly complex neural networks that can perform on par with uh, theoretically whatever you like if you had the hardware and data to do it. But anyways, let's look at a slightly more difficult sample and then we'll end this tutorial. We'll see that this network, this is an actual network. It has 4 input neurons, 2 neurons in the hidden layer. The hidden layers are any layers between the input and the output. They're just called hidden layers. There's 1 in this case, and and this hidden layer has 2 neurons. The output we'll call F1, which is our final neuron, and we only have 1. So in this case, we want to, let's say we want to we know how to update F1 and F2. You just apply the same exact principles as you had in the single neuron example. You run your sample through, you get your relative values for A2 and A2 and A1 after they've gone through the activation function, and then you just multiply them against F1 and F2 and do the same exact thing over here. But let's say you have 2 layers in this case, and you don't just want to get F1. You'd also would like to get A1W2. So A1 means it's the weight, the first weight that's connected to our neuron A1. That turns out to be almost the same as how you would get your value for F1, FW1. So let's take a look over here. We have the equation written out, and we'll just talk about what all of this means. I try to make them in big font so they're easy to read. I didn't use any fancy notation. This is plain, simple English for anybody can understand. So if we want to update our weight that's in the first layer, A1W1, we take that original weight value and subtract it from this term, which is going to be our learning rate times the output of A1, whatever the output is, after it's gone through the activation function, minus the target of A1 times the input. That should look very familiar. That's exactly the same equation as we had over here. We had the learning rate, the error term, times the input. But you're probably wondering, how do we get the target value for A1? Because how do we know what these weight values should be adjusted for our neuron A1 so that its value decreases or increases accordingly, so that our error here in our final neuron goes down for all of our input samples? Well, to get our target, it's actually pretty straightforward. We just get our original A1 value. Now, it's really important to remember in this case, the A1 value is literally just a copy. So the original stays here, up here, and we just make another copy. So whatever A1 was. So we take A1 minus F1, whatever the output of the final neuron was, minus the target for the final output of F1. And the target, once again, it can be anything you like as long as it's within the output range of your function. And then we multiply it instead of the input value, which would be A1 in the case of a single neuron. If we were just training F1 or the weights for F1, we actually multiply it by its corresponding weight. And the reasons for that is because we want to know the target value of what A1 should be aiming for. Once we have that, we just plug it all in. So A1W-1 should equal the original value of that weight minus the learning rate times A1 minus the target. Now remember, A1, we had an extra copy up here. So we use that original value. The copy is already modified because T is a different value. So it's a little different. Minus the target. And A1 minus the target, which is over here that we got, minus its input. And that's it. And then this is just rewriting the entire equation again. It's the same exact thing as the one above, but instead of having A1 minus T, we explicitly write what it looks like. It's going to be A1 minus everything in parentheses over here, which is A1 minus F1 minus TF1 times F1 FW1. God, that is a mouthful. And that's it. That's all you need to know in order to update this weight relative to this neuron and this input sample. Of course, if you had a different input sample, you just substitute the appropriate value for it. And this is universal. You can apply it to any size network that you like, with any number of layers, any number of neurons, any activation function. It always works as long as you adhere to these general rules. And if you do, you'll get a function that looks, or not a function, but a network that can do cool things like predict handwritten digits, recognize faces, um, maybe even generate text, depending on how complex you want your model to be. Anyways, thank you so much. Let me know if you have any questions, guys. Leave them in the comments. I'll be happy to look them over and give anyone any kind of feedback that they need / want. Um, and even make a follow-up video if there's confusion on what I was talking about. Great. Alrighty. Thank you so much. Bye-bye.